Welcome back. Before approaching the end of scalar tensor theory, let's make a little recap of what we covered during the lectures. So as we have seen, scalar tensor theory has a very broad class of theories which involve a tensor field, which is going to be our metric, and a scalar field that, in the purpose of these lectures, is meant to reproduce, for example, dark energy, or in a more general sense could be also used to generalize gravity. Okay, so that's our action for typical scalar tensor theories, actually for scalar tensor theories as they are constructed, in which we have our usual invariant four-dimensional volume element. We have an arbitrary function f, which is a function of a scalar field and of the Ricci scalar. So you see there is going to be a coupling, if one wish, between the field and the gravity. This would be our generic modification of gravity. And then we have another term which involved a kinetic term and an arbitrary function, both referring to our scalar field. Okay, so an arbitrary function of the scalar field and a kinetic term of our scalar field, plus the usual matter term, right? That's the action of the matter, which is sourcing gravity and the dynamics of the field. Then what we did was to perform a conformal transformation to go from the Jordan frame to the Einstein frame, such a way that we recover through this transformation, where given this construction, this is possible through this conformal transformation, okay, where our conformal function is the derivative of the function f, this guy here, with respect to the Ricci scalar. And in this step, you see, we recover the standard general relativity form for gravity, and we have additional terms. We have our kinetic term, and for this specific case of the function f that we have chosen, we have the appearance of a potential. Here you see u, here you see v, but you know that when using f here and performing our conformal transformation, both the potential and the field get relabeled, so to say. Okay, so our little phi becomes the big phi, and our field and our potential u becomes the potential v. Okay, just relabeling as we have seen, just the change of frame as we have seen. Then what we did was to introduce a coupling strength Q, which is defined in this way, that to obtain something analogous to the, or actually identical to the coupling strength that we have seen in coupled dark energy. And if we are imposing Q to be a constant, then we have an explicit form for f, which is this one, and for the function psi, this guy here. Okay? Once we have that, we can therefore plug in our expression to have an explicit form for f and xi. Once we have that, we can go back to our Jordan frame, as we have this relationship that we can make explicit here and here, and we obtain this expression, where you see that the coupling term, which was appearing here, is kind of disappeared. So we are going to have conserved entity. That's because we went back to the Jordan frame, whereas the coupling is going to appear in the parts which will be represented by modified gravity. Okay, so you see you can shift the coupling term from the coupling with matter here, meaning standard gravity, a field plus you know, the dynamics of a fluid here, and a coupled dark energy with the matter term, to a theory in which we have a conserved matter field and a modification of gravity. Okay, but what we did in this step, yes, we went back to the Jordan frame as we had in this form, but through this trick, we basically managed to express the modification of gravity with respect to Q, which is representing the coupling between the field phi and the matter content. Okay, so that's what we have seen during the past lectures, on top of which we have also seen how this theory can reproduce f of r gravity, coupled dark energy, and so on and so forth. Okay. Now, before moving on and close this topic, I would like to stress a little bit more the meaning of the coupling term, okay, and how is this related to the fifth force. That's what I'm going to do now, okay? So, what you do in general relativity if you want to understand what is the effect of gravity on a field in the weak field limit? Well, you apply the weak field limit, which means that you get your metric tensor and you expand it to first order. So you keep only first order perturbation terms, okay? The perturbation terms that are at first order. So what is our metric? Well, that's our metric G that contains the coupling, and therefore after the conformal transformation it acquires this term here. Okay, so that's our metric. After when we go back with the terms Q, we have this additional term here. Then what we do, as I said, we use perturbation theory and we keep only first order term. Therefore, we have our G mu nu, which is equal to the first order term plus higher order terms. So this is kind of familiar from general relativity. And then we can as well expand this guy at first order. That's because Q, with this theory, Q is going to be small, otherwise we will break the constraints on local gravity that we have. Therefore, Q must be small, and therefore we can expand this guy at first order as well. Okay, so we have the expansion in the perturbative approach for phi, and just a Taylor expansion for this exponential given Q, which is small. Then you just make all the multiplications of the case here, and you keep only first order terms. First order terms that give you that. Okay, so what's the difference with respect to general relativity? That there is a guy in addition, okay, this one here. What's the effect of that? Well, it is going to give you a modification of the gravitational force that is experienced by a massive body, for example. So you see that in general relativity you would not have this term, there would be only that. And you know that this 2 phi is associated to the Newtonian gravitational potential. Newtonian gravitational potential that in general relativity would be only this term. But now we have this guy on top. Okay? So you see we manage in this way, by using this perturbative approach at first order, we manage to recover our Newtonian gravity plus a correction term which is due to the coupling, you see the terms Q, with the field phi. Okay? And once we have this effective potential for this, now we interpret this gravitational effect as a force, we can get the acceleration on the body. And therefore, you know, the acceleration of the body is given by the gradient of the potential. So if we plug now this potential into here, we are going to have a force which is the standard Newtonian one plus a force that is associated to the coupling term, which is this extra force. That's the fifth force that we were talking about, which is due to the coupling between the field phi and matter. Okay? So that's where, if you want, is a more practical way of looking at this coupling term, of this coupling between Q and phi with respect to a force. Honrdeski theory. So in our path, you have seen we moved from the simplest theory of gravity that we have, meaning GR. We introduced a scalar field, dark energy, in terms of quintessence, and then we start to generalize our theory by introducing coupling between the scalar field and the matter term, and we introduced a f of r theory up to the point in which, in the path of our generalization, we encounter scalar tensor theory. Now you could ask yourself, can we continue with that? Yes, we can be even more general. And here it comes the Honrdeski theory, which is the most general scalar tensor theory, which provides you with good equation of motions. Good equation of motions means that there are not going to be ghosts or instabilities of that sort. So a good theory, as we can classify it. So which kind of generalization could we do? Well, for example, here is like a set of various terms that you could introduce, so they are arbitrary. But as we said, we don't want to introduce instabilities. And what are, first of all, instabilities? Well, we can distinguish them into different classes. One are classical instabilities. For example, that would be, for example, a theory in which your cosmic expansion gives you an acceleration which is infinitely fast. Okay, so you have a universe which is unstable. In the same way, blows up. Okay, not what we have. That's a classical instability. Or your universe maybe is expanding, but then it collapses very fast. Again, another kind of instability. You don't want that. Okay. Another kind of instability might be something more intrinsic, or if you wish, even more to the core of physics, which are of quantum nature. I give you an example here, and you know, for example, that electrons can decay from higher orbitals to lower energy ones, right? And every time they are going to emit a photon. When do they stop? When they hit the ground level. Okay, so they decay to lower energy levels, they emit a photon, emit a photon, emit a photon, and boom, they arrive at the ground level. And they cannot emit any more other photons. So you see there is a bottom line in the energy level. So there is an energy bound, a lower energy bound in the theory that is describing basically these sort of quantum transitions. But if you have a theory in which there is not such a bottom floor for your energy level, then what would happen? You would have that your electron is going to decay to a lower energy level, emit a photon. In the case, it can emit a photon, it can emit a photon, it can emit a photon, and if there is not a bottom, there is not a ground level, then this process can continue at infinite. What would it mean? That you would have an atom which is an infinite source of light. Okay? And remember that each photon is a particle. This would mean that you have an infinite amount of production out of nothing. Okay? You would have like a system which has can provide an infinite number of particles. Okay? Without any limit. And these are what are called the ghosts. Okay? And therefore you don't want that. You want theory which do not possess any classical instability, neither a quantum instability. Okay? How can you do then? How can you choose? You know, these are just three examples. You could make other mixture of these terms. How can we do then say, okay, this is a good combination, this is a bad combination? Well, thanks God, or thanks to physics, better to say, there is a way out, which is the Honrdeski theorem. Okay, so there is a theorem that tells you that every Lagrangian that leads to equation of motion higher than second order do not have a ground state. So if you have an equation of motion, so if you have a Lagrangian that leads you to an equation of motion which is higher of second order, there is not such a ground state, and therefore ghosts might arise. Okay, your theory is a bad theory. Okay, and just to give you, of course, I'm not going to prove this theorem, but I can give you just a way of, an intuitive way of understanding why this comes about. And for that, let's just keep a theory which is of third order. Okay, that's not a good thing to do, because if you have the order which are uneven, so 3, 5, 7, and so on and so forth, then you end up in having a problem with time and reversal symmetry. That's something you would like to avoid. If you go to fourth order, where you don't have this time reversal symmetry problem, then you have 4 degrees of freedom. Would be phi 1, phi dot, phi dot dot, phi dot dot dot. Okay? What does it mean? It means that your phase space, remember that the phase space is the one describing the trajectory of possible physical evolution for your system, would be of a dimensionality which is extremely large. Okay? The larger is the dimensionality of your problem, the likelier it is that in your phase space you're going to you have your trajectories which are escaping to infinite. Okay, and we might also encounter singularities. This will give you the problems that I mentioned earlier. Moreover, something, if you wish, more trivial, look how many initial conditions we have. 4. What are you used to give as initial condition? An initial location and an initial velocity. Right? In all physical systems that you know, that's what you need. That's why in physics we tend to stick to second order differential equation, because we set just a system with some initial value and an initial velocity. The rest follows, is given by the equation of motion. Okay? Bottom point, bottom line, we have a Honrdeski theorem that states that we want to have second order differential equation for our equation of motion, not higher. But one have to be careful, because you might end up to build up a theory which looks like third order or fourth order in terms of derivatives, but actually is might be reduced to a combination of more field with described by second order differential equations. Okay? To show that it's easier to do the process the way around, meaning we can start with a theory based on two fields. Okay? You see, we can introduce how many fields we want in our theory. Could be also a complex field, one but complex, that it would be equivalent to have two linear, two real fields. Okay? Anyway, let's start with these two linear fields, phi and phi. And what we are going to have them described by two Klein-Gordon equations. Okay? Second order, all is good, all is nice. But then you know that out of two second order differential equations, you can combine them together to create a system of higher order equations. Okay? A differential system, one equation which is of higher orders. We did this trick the way around when we started from the second order differential equation of our Klein-Gordon field, and we split it into first order differential equations. Okay? You see, you can do you can go in one direction or another one. Therefore, you understand that there is the equivalence between an higher order differential equations, an order which is higher than 2, and a set of differential equations with lower orders. Okay? Therefore, it doesn't mean that higher order is necessarily bad. It just means that if you can have a theory which ends up to be of higher order, but which can be split in more fields, then it's still a valuable theory. Okay? So just take care of it. Good. Little summary of this part. We can generalize as we wish. We have not the freedom of the universe, because what we want to do is to create something which has a physical meaning, and it avoids ghosts, meaning we want a theory which has equation of motion up to second order, such that this avoid ghosts. And this is a statement given by the Honrdeski theorem. Now that we know that we want only second order differential equations, such to avoid ghosts, we can ask ourselves, what is the most general Lagrangian that satisfies this condition? Well, it's this one. Okay? It's this one that has been first put together by Honrdeski. Okay? Honrdeski was a physicist, well, actually still alive, so he's a physicist, and he defined this action. This action that you see contains the usual meta term, it contains the usual invariant for volume element, and it contains the sum of four Lagrangians. Four Lagrangians that depends on a scalar field and on the Ricci tensor. So this expression gives you the most general scalar tensor theory, which leads to second-order differential equations for the equation of motion. Okay? That's what it is. If you look at it, it looks like cute little equations, but if you take care, there is this summatory, and in the end, the Lagrangian is going to be the sum of these 4 Lagrangian. If you put them all together, it's quite a beast. Okay, so it's quite a complex object to deal with. And this Lagrangian is basically based on these 4 arbitrary functions, k, g3, g4, and g5. The names k, g, and the numbers are given by historical reason. Just keep in mind these are four arbitrary functions that you can find here, and then where else. And then here we have the derivative of the function g4 with respect to x and g5 with respect to x, where this x guy here, you see, it appears in all as an argument in all function, is a kinetic term of the field. Okay, so these are arbitrary function of the field phi, and must contain, or if you a kinetic term for that very same field. Okay, that's what they are, and they must be of this structure. Okay, so you see we have just L2 is just this function. L3 is a minus, and then it contains a kinetic term here. A kinetic term is contained here. So these two guys are responsible for kinetic terms in your action. Whereas these other two functions, g4 and g5, you see they are expressing with respect to R, so that's the Ricci tensor, and then we have g mu nu, we have the Einstein tensor, both of which represents gravity. Okay, therefore these two guys represents the coupling between the scalar field and gravity. Okay, so out of these 4 you have 2 families. The first 2 represents kinetic terms, and the second 2 represent coupling term between the scalar field phi and gravity g, and gravity to the Einstein tensor. Now that I've shown you this Lagrangian, you should complain because I told you that this should give you equation of motion that are of second order, but you may notice that it contains terms such as this one, for example. And write it also here. You see that this box operator contains double derivatives with respect to phi. Sorry, the double derivative with respect to time of phi. And whenever you introduce this Lagrangian in the Euler-Lagrange equation to derive the equation of motion, you know that we are going to have additional time derivatives of this term. I mean, the entire Lagrangian, of course, but in particular of this term. That gives you derivatives, time derivatives that are higher than second order. And therefore, you might say, okay, then the Honrdeski theorem is not satisfied, we are going to obtain ghosts in our theory. But actually, the construction of this Lagrangian is such that there is not only this term, but there are also other terms that leads you contribution that cancel one each other once they are introduced into the Euler-Lagrange equation, guaranteeing to obtain such that you are sure to obtain the equation of motions up to second orders. The higher order terms are going to cancel each other. That's why you cannot touch at all this structure. For example, if you have 1/6 here, this 1/6 is introduced exactly to have the right number to cancel some other term. Okay? This is your Honrdeski action. Now we can give a look at a few examples, okay? And I'm going to show you how general relativity is contained in the Honrdeski theory, as well lambda CDM and various other theories. Let's give a look. Case number 1, standard gravity, meaning general relativity with a non-canonical kinetic term is the one for which G4 is equal to 1/2 and G5 is a constant. Just play the trick, substitute, set G4 equal to 1/2, it means that you would have 1/2 R. 1/2 R, you see, is the guy that you expect, is the Ricci contribution that you expect in the Einstein tensor. And then you have derivatives with respect to the kinetic term of G4, but that's equal to 0. So you have only this contribution. If G5 is constant, this derivative here is going to be equal to 0, so all of this disappears, and you are left with this guy, constant, and the Einstein tensor, where the Ricci tensor is going to play together with this one, okay, to give you a contribution which is the one given by that you find in Einstein field equations. But, as I said, with a non-canonical kinetic term, because we didn't touch these two guys. Okay, so if you set up G4 and G5 in this way, okay, then you get gravity, standard gravity, but the fluid has a canonical, has a kinetic term which might be not canonical, because, for example, we can choose L2 like this one, where we have our kinetic term. I recall that X is this guy here, so just have the kinetic term minus V, so that would be your ideal fluid, for instance, but could be something non-canonical, like this guy, where we have, for example, x to the power of 3, okay? And you can invent whatever you want. So here it still retains flexibility. This is just to set gravity as a general relativity. Then an example. If we want to have instead a canonical form for your fluid, then K must be equal to that, and you recognize this is just a typical canonical form, and G3 has to be a constant. Okay? But you say, but there is this box operator. Yeah, but remember, if you recall what we did to the conformal transformation, that there is always the way to put this box operator in terms of a standard kinetic term, which would go together with this guy here, okay, such that you obtain a canonical fluid, a Lagrangian for a canonical fluid. If you want lambda CDM, then you just have to use the condition 1, meaning G4 and G5 equal to 1/2 and a constant respectively, such that you have standard gravity, plus you want a kinetic term which represents the one of dark energy, of the cosmological constant, and therefore your K must be equal to -2 and a constant. Whenever this is the case, you just have your fluid that's equal to 0, and you just have that. Okay. If you want Brans-Dicke theories with a non-canonical, which might contain a non-canonical kinetic term, you just have that G4 must be only a function of phi, so G4 would not contain the kinetic term, and G5 should be a constant. Then you recur Brans-Dicke. If you want to have the original Brans-Dicke theory, meaning with a canonical fluid, with a canonical Lagrangian for your fluid, then K must be equal to that, G3 must be equal to that, and G4 must be equal to that. Just make the substitution in your expressions up here, and you will realize that you get just the standard Brans-Dicke theory. If you want f of r, then G4 must be equal to this exponential, K must be equal to that, where we have defined phi such that it equals to that. Okay? Whenever this is the case, then your Honrdeski theory represents f of r gravity. Okay? So you see we can have a standard gravity, we can have a standard canonical form, we can have lambda CDM, we can have Brans-Dicke, we can have the original Brans-Dicke, or we can have f of r gravity. And of course, you can have way more, also other set of theories, so something which goes beyond what we've seen during the previous lectures. So what is the big fuss about this very complex Lagrangian? Well, first of all, we identified the most general scalar tensor theory that given you ghosts, and that's extremely good. But on top of that, it gives you also features that are not present in the standard scalar tensor theories that we have seen in the previous lectures. Namely, in certain cases, according to the function k, g, etc., that you can choose, you might obtain the propagation, the speed at which the gravitational waves propagate, which is different than the speed of light. Okay, so you might get gravitational waves that propagate through space-time with a speed that is different than the one of light. And that's a key difference with respect to the theories that we have seen before. How does it come about? Well, let's first of all give a look at how this is done, how the speed of light is obtained in general relativity. To do that, you know that you have your metric that contains your perturbation of the time components, the perturbation of the space component, and what you do to derive the properties of gravitational waves is to get your metric. You apply, you use a perturbative approach in which you have your background metric. In GR, I'm sure you use the Minkowski spacetime. In a cosmological constant, you would use the Friedmann-Lemaitre Robinson-Walker metric. This would be the metric for your background, plus a perturbation term that we call H. Okay? After you go in the TT gauge, your H will look like that. And the equation of motion for your field, so the Einstein field equations that you linearized with this perturbative approach, will look like that. You see, we have a box operator applied to your perturbation tensor equal to the constant factor k and the energy momentum tensor, which is sourcing the perturbation. Now, what tells you this equation for the speed at which your perturbation is meaning gravitational waves are going across the sky? Well, if we consider vacuum, this guy would be equal to 0. You would have box operator of H equal to 0. That's an harmonic function, and which solution is an exponential, and in the exponent you get c as the speed, the propagation of your gravitational waves. Okay, so in GR again you get your metric, you use a perturbative approach, you obtain your linearized Einstein field equations. In vacuum, so with this guy set equal to 0, there is an harmonic function which solution tells you that the speed at which the perturbation is moving across the spacetime is the one of light, c equal to 1. Okay? You should do the same in Honrdeski. I'm not going to do that because it's a bit horrifying in terms of mathematical steps, but conceptually you do exactly the same. Perturbative approach, and you obtain the speed, a solution which is similar to this one, but the speed at which gravitational waves are going across the spacetime is actually not c, is equal to c plus another term. Okay? Therefore you already know that there is going to be a strong constraint on the possibilities for the functions g4 that appears here and here, and g5 that appears here, here, and here. Okay? And these observations comes from gravitational waves measurements. You know that in the past we have observed a merger between a neutron star and a black hole. Why we have this fancy combination with a neutron star and a black hole? Why not a black hole merger would provide us in observation constraints? That's because if you have a black hole merger, you do not obtain any emission of radiation. You would only obtain gravitational waves, but not emission of photons. Therefore, you would have an event in which you cannot compare the speed at which photons and gravitational waves are going to reach you. And therefore, you cannot see which one is the faster. Okay? Whereas if you have a neutron star black hole merger, you have a neutron star that in the process of getting merged can emit radiation, because the result is not embedded in an event horizon and radiation is free to travel. Therefore, during this event, you are going to have the simultaneous emission of a gravitational wave and of photons. The two are traveling across the universe to reach our laboratories, and people measure the difference between the speed at which measure the difference of the timing of arrivals of the two signals, photons and gravitational waves, and that's the difference that they measured. So the gravitational waves arrive with a speed which is the one of light plus or minus 10 to the minus 15, which is basically 0. Okay, that's the one of the tighter constraints that have ever been obtained in physics. So you see that if we are dealing with such a theory, we need terms that this G4 and G5 must be such that this constraint is satisfied. Meaning this term should be equal to 0. And this guy, no, up to this one, so the 1 should be there. So you understand that for this guy to be equal to 0, then these two conditions must be met. Okay? So the derivatives of G4 of G5 with respect to the kinetic term must be equal to 0. You see, equal to 0, equal to 0, equal to 0, then this guy is equal to 0. Again, what does it mean if these derivatives are equal to 0? It means that G4 must be a constant and G5 must be a constant. Okay? This is constraint coming from these gravitational wave measurements simultaneous to the emission of photons. Okay? So you see, we moved on to build up a theory which is the most generic one, but most of those terms got killed. So this guy and this guy are going to be equal to 0. This must be a constant and this must be a constant. Okay, so you see we build up these gigantic machineries, and then one observation basically reduces the complexity to what we actually are observing in the universe. So this is our Honrdeski action.